Last chapter of this semester, chapter 9, start with section 9.1. We're going to be talking about vectors. Most of the quantities that you've dealt with are what are called scalars. A scalar quantity just has magnitude. It just gives you some measurement of how big something is, how much there is. A vector has magnitude and direction. So it's sort of like, if you want to look at it in one dimension, you can think of the number line. So here's the points 3 and -3 on the number line. In either case, I have to move 3 units away from 0 to get to that point. But here, I moved 3 units to the right, and here, I moved 3 units to the left. So if I just need to know how far I went, 3 is a good enough value. That's the scalar. It's measuring the magnitude. If I need to know which direction I went as well, I need to use a vector to give me both of those things. So in 2 dimensions, we usually go with a geometric interpretation. If I have 2 points, A and B, sitting out in a 2-dimensional space, just in my plane, I connect the 2 with an arrow, and I've got the vector AB. It has some kind of a physical length I can measure, and I've introduced a direction by saying I started at A, I traveled this direction, and I ended up at B. And you'll see this notation, absolute value bars, to indicate the magnitude, which could be measured not unlike the way we were measuring the length or the magnitude of complex numbers in the last section. We're going to see some nice overlaps there. You also see that talking about the length of the vector. But vectors can be equal as long as they have the same length and direction, same direction of magnitude. So that vector, that vector, that vector. Assume that I drew these well and that they're all the same, exact same length and going the exact same direction. They would all be equal vectors. Even though they didn't start at the same spot, we still consider them all equal if they've got the same length and the same magnitude rather, and they're pointing in the same direction. And we can use this to add vectors too, right? If I had 2 vectors, AB and BC. So here's my points, A, B, C. The vector AB starts at A, proceeds to B. The vector BC starts at B and proceeds to C. And this should really be a new vector, AC, which starts at A, proceeds to C. You get the same kind of thing. So if one vector is immediately followed by another, this works out really nicely. And I can do that to add up vectors. If I don't have 2 vectors that are lined up like that, where I've got A to B and B to C, suppose I just have 2 arbitrary vectors. Let's call them U and V. So these are vectors. Here's U, and here's V. Now, they're equal to any other vector which has the same length and goes the same direction. So what I can do if I want to add these 2 up, I can say, well, what if I started at the tip of one, and then I moved these around, shuffled this one over to here so that it ended up there. What you can get is this nice picture. So if I've got, let's make that a little shorter. There's U, and I'm going to shift this down to here. So there's V. And what I do, trace out the parallelogram that would be formed by the 2 of these. The diagonal of that new parallelogram. u plus v. I can do that with the parallelogram, or I could do that with, if I took this vector, placed it over here, it would be the same thing as going from the tail of one to the beginning of the other. You get the same displacement idea that we had in the last slide. I could also take a vector and I could multiply it by a scalar. So if I had some vector u, there's 2u. It's twice as long, and it points in the same direction. There's 1/2 u. It's half as long, and it points in the same direction. So that gives you kind of a general idea of what vectors do. Again, your text has much greater detail regarding the constructions of these things and a lot of extra examples. But we want to go over, too, how I can represent this in the coordinate plane. So if I have a vector v, your text uses these angled brackets to record that it's a vector. And what this is really saying is this vector, if I start at some point, I'm going to travel some distance a in the horizontal direction, some distance b in the vertical direction, and that's going to give me my vector v. So I get a horizontal and a vertical component, ordered horizontal first and then vertical second, just like what we're used to. But what's nice is that I can always represent a vector, as long as it's got the same length and direction, I can move it wherever I want. So there's no reason I couldn't just go to a good old coordinate plane, have a and b, and have the vector v represent the vector that starts at the origin, goes out to the ordered pair AB in that direction, and given that length. So you can set that at the origin. You could also be given 2 points, what we call the initial point and the terminal point, and find a vector that goes between those two. So if I had initial point, say -2, 5, and terminal point 3, 7, the vector between those two would need to say, well, if I started here, how far do I have to travel horizontally to get here? Three minus -2. And if I started here, how far do I have to travel vertically to get here? 7 minus 5. So the vector with this given initial and terminal point would be 5, 2. Now we can represent that many different ways, but we do tend to want to do it by placing these things at the origin when we can, just because it's convenient. Now I can also find, if I called this vector v, I could find the magnitude of v. And because I could, again, translate this back to being at the origin and being a line connecting 0, 0 to the point 5, 2, the Pythagorean theorem comes back, same as it always has. So the magnitude of this one would be square root of 5 squared plus 2 squared would be the square root of 29. So this vector, 5, 2, if I have it go with this initial point and this terminal point, if I have it go from the initial point 0, 0 to the terminal point 5, 2, it doesn't matter. All these vectors are going to be the same. They're all going to point in the same direction, and they're all going to have the same magnitude, square root 29. So once we've got this nice coordinate plane representation, suppose I had two vectors, u plus 2, -3, and v equals -1, 2. I could add these guys, subtract them, multiply them by things. So I could take u plus v, and we're just going to get addition of components. 2 plus -1, -3 plus 2. So I've got 1, -1. much nicer than just doing the purely geometric representation. We can calculate these things pretty quickly. I could have 2u minus 3v. So that's going to be 2 times 2, negative 3, minus 3 times negative 1, 2. So 4, negative 6, minus negative 3, 6. 4 minus negative 3, negative 6 minus 6, 7, negative 12. So the arithmetic's pretty straightforward. One last piece of notation that shows up sometimes. Again, it can be slightly confusing because of some overlap with the notation that we used earlier for complex values. We have unit vectors and the zero vector. So the zero vector is just the vector 0, 0. Sometimes it's just written as a 0. And it's nice because if you have a vector u and you add the 0 vector, you just get the u back. It gives us an additive identity, something that we can have a 0 that's well defined. Unit vectors are 1, 0 and 0, 1. And these tend to be written as I and j. So you'll notice the magnitude of I equals the magnitude of j, and they both equal 1. They are of length 1, the unit of measurement in the real numbers. So that's why we call them unit vectors, but it's handy because suppose I had u was 5, negative 8. That's really the same thing as 5 times 1, 0, plus negative 8 times 0, 1. So sometimes you'll see these vectors written as 5i minus 8j. We can represent them this way, and sometimes for some of the operations we'll see in the next section, it helps us keep track of it. The I and j are also handy if we want to look at the components of a vector. So if I had some vector v, points a, b, I could write this with my i's and j's as a I plus bj. Your author puts these in boldface. Sometimes you'll see a little arrow over the top to indicate that those are the unit vectors, and not just arbitrary variables. And we can compute the magnitude of v. Right, we know how to do that. Square root of a squared plus b squared. Now, if I take and view this in the coordinate plane, there's my vector v. There's some angle theta, smallest angle formed between my vector and the x-axis there, the horizontal axis. And a little bit of trigonometry will show you that if these are your components, that a is the magnitude of v cosine theta, and b is the magnitude of v sine theta. So we're back to a similar representation to what we had for our complex numbers. V equals the magnitude of v. I guess we'll put arrows here just so we know that we're talking about vectors, times the cosine of theta times I plus the magnitude of v sine of theta times j. So we can find out how far I traveled horizontally, how far I traveled vertically, relate that all back to that angle. Again, it's coming back to the trigonometry that we've been working on all semester. So in the next section, we'll look at how we can do some computations of these kind of components and what some of the applications are for these vectors when we are actually modeling things like some physics problems.